Hydroelectric power is the largest source of renewable green energy and accounts for about 20% of all electricity produced globally. The technology involved is proven. Hydroelectric power plants are large and involve huge capital investments. They also tend to affect the local ecology once the dams associated are flooded. Smaller micro hydropower systems, which generate less than 100 kilowatts, are more cost-effective to produce renewable energy in rural areas, which are near streams and flowing rivers. This video presents a new invention on power generating systems, which channel hydraulic inflow from a water catchment area into a discharge hollow channel, and then into a discharge pipe before the water is discharged to lower ground. The system operates within the water catchment area and is built higher than the highest water level. The walls are formed with nozzles so that jets of water flow from outside the inflow dam into the internal cavity and onto the impellers of the turbine. The rotating turbine is connected to a generator located above the water level, which generates electricity. The water downstream of the turbine flows through a discharge channel into a discharge pipe before the water is discharged to lower ground by gravity or siphon. In the second variation, the nozzles are in 2 or more rows and correspond to the number of turbines. In the third variation, the impellers of the turbine are elongated and parallel. In the fourth variation, the nozzles are also elongated and generate water jets with elongated cross-sectional areas to each elongated impeller of the turbine. The inflow dam has a rotatable sleeve supported on the shoulder, located below the nozzle or seal and registered to the apertures. When the apertures are not in register with the nozzles, water is prevented from flowing through the nozzles during maintenance. The inflow dam is submerged in water, and the internal cavity of the inflow dam is designed to be filled with water to turn impellers of the turbine to generate electricity. The discharge channel after the turbine acts like a draft tube, and it helps create suction and increase the dynamic hydraulic flow and head. The sleeve is designed to extend above the top end of the inflow dam so that the water is prevented from entering the inflow dam during maintenance. A seal may be provided between the sleeve and the external surface of the inflow dam. In use, a fluid cylinder may control the sleeve for regulating the head and amount of water flow to the turbine. This system allows the user to select a number of the above systems to operate according to the electricity demand and available water head or hydraulic flow. This allows some of the inflow dams to be closed for maintenance without disrupting the supply of electricity from the hydroelectric system. The above network system is only one or part of the Galaxy hydroelectric inflow dam network systems. Many reservoirs are built to store drinking water. However, only a small percentage is sent to the desalination plant. The rest remains untouched. We intend to turn this high percentage of unused water into hydropower. The main objective is to harness the gravitational potential energy in the water by moving it from point A to point B. The final destination will be the water desalination plant. We can also have the option of channeling it back to the first reservoir or sea. For a shallow water solution, digging a large hole or installing a large water tank underground allows it to fill with water and accumulate water pressure. Install the inflow dam and the rest as usual. Using our hydroelectric inflow dam system, harnessing huge unlimited renewable energy can be a reality. The hydroelectric inflow dam system is cost-effective and can be built in large scale and can be rapidly increased. Using our invention, we help to lower production costs to develop purified drinking water using desalination plants. If you can solve the power, You can solve almost everything.
Okay, now I want to try and help you understand some of the rules that apply to electricity. First of all, you know what happens when I plug this in. And you may know that what I'm going to plug it into is 110 volts. What's a volt? Well, a volt is a measure of energy. But you'll notice that when I plug this in, something else happened. Current flows through here. We measure current in amperes. You may have heard amps. Somebody's talking about electrical stuff. Amperes run through there. So the voltage makes it flow, and the amperes are the electrons. It's actually how many electrons are flowing. So it's like if I had a tube of water, and if I had the tube perfectly level, the water would stay in the tube. But if I went like this, the water would flow out of the tube. The difference in energy is the voltage, and that's what makes it flow. The actual material is the current. So watch what happens here. I plug this in, and as you sort of suspected, all of the bulbs burn. And they burn the way you've seen light bulbs like that burn. Now let me show you something else that's kind of interesting. These bulbs have relatively high resistance. And what that means is that it's kind of hard for the electrons to fight their way through the light bulb. Here's a light bulb that has a lot lower resistance. It doesn't oppose the electrons as much. So I'm going to take one of these light bulbs out of here. I'm going to put this one in place of it. Watch what happens when I plug it in. Now remember, this one has less resistance. This one doesn't oppose the flow of electrons as much as these do. And look what happens. Wow, a lot brighter, isn't it? Why is it brighter? Because most of the electrons are going through that bulb. Well, you think about it. If you had a choice of going through a place that's hard to go or go through a place that's easy to go, where are you going to go? Most people are going to go through the one that has the least amount of opposition. And that's why light bulbs have different brightnesses.
Electromagnetic induction. Prepare a circular coil out of copper wire. Connect the two ends of this coil to the two terminals of a sensitive galvanometer with a scale having 0 at the center. This closed circuit is shown in the diagram. Note that this circuit contains no source of electricity and the galvanometer shows 0 reading initially. Take a bar magnet NS and move it swiftly towards the coil with its north pole facing the coil. You will observe a deflection in the galvanometer when the magnet is moving. The deflection indicates that current is set up in the coil. Now, move the magnet away from the coil. The galvanometer shows again a deflection, but in the opposite direction. This means current is set up in the opposite direction. If you hold the magnet with its south pole facing the coil and repeat the above steps, the deflections are again observed, but are reversed. Similarly, motion of the coil itself also produces deflections in the galvanometer when the magnet is kept stationary. Do you observe any deflection when you just hold the magnet stationary near the coil at rest? No. A relative motion of a magnet and a coil induces the current in the coil. The current produced by a relative motion of the coil or the magnet is called an induced current and is said to be set up by an induced electromotive force, EMF. The production of an induced EMF in a coil in a closed circuit by the relative motion of a magnet and its coil is called the phenomenon of electromagnetic induction.